Have you ever wondered how computers can recognize faces, understand handwriting, or even predict the weather? It's all thanks to neural networks. Over the next few minutes, I'll break down the 6 essential things you need to know about neural networks. And I promise, no confusing jargon, just simple explanations. Neural networks are at the heart of AI, mimicking the way our brains process information. But what exactly are they? How do they work? By the end of this video, you'll not only understand the basics, but also see how these networks power some of the most amazing technologies around us. If you're as excited as I am about learning this, hit that like button and let's dive in. First, think of a neural network as a series of layers: the input layer, hidden layers, and output layers. Imagine the hidden layers as chefs in a kitchen, transforming raw ingredients into a delicious meal. Each layer processes information and passes it forward, enabling the network to make sense of complex data. Next, neurons. These are like tiny decision makers, each holding a number between 0 and 1. For instance, should you go surfing? If the waves are great, 5 points. The crowd is low, 2 points. And there are no sharks, 4 points. You'll likely grab your board. Think of these weights as tuning knobs that determine how much each input matters, and the threshold as the point where a decision is made. Neural networks learn by adjusting their weights and biases using data. This process is called supervised learning, where labeled data teaches the network to improve its predictions. It's like training a puppy to fetch. You reward correct actions and gently correct mistakes until it gets it right. Through multiple iterations, the network fine-tunes its parameters, just like perfecting a recipe after repeated tastings. Data flows forward through the network in a process called feed-forward, generating predictions. But what happens when it's wrong? That's where backpropagation comes in, a method to tweak the weights and biases to reduce errors. This is done using the gradient descent, where a network adjusts step by step to minimize errors, much like fine-tuning a complex machine. This cycle repeats until the network gets really good at recognizing patterns. Finally, not all neural networks are the same. There are feed-forward networks, convolutional networks for images, and recurrent networks for time series data like stock prices. Convolutional networks are great for identifying objects in images by recognizing edges and patterns. For example, they power facial recognition systems. Recurrent networks excel at processing sequences like languages or sales data. Think of predictive text or stock price forecasting. Each type is tailored to specific tasks, making them incredibly versatile. Activation functions are what make neural networks powerful by introducing non-linearity. Without them, neural networks would just be a series of linear equations, unable to handle complex data. Think of them as switches that determine if a neuron gets activated or not, much like a circuit turning on or off. Rectified linear unit, for instance, is widely used today because it trains faster and performs better than other methods, like sigmoid. A well-trained neural network finds a balance between memorizing data, overfitting, and generalizing to new data, underfitting. Overfitting is like memorizing exact answers for a test, while underfitting is like understanding so little that you can't answer any questions. To avoid overfitting, techniques like dropout, regularization, or using more diverse training data can help. Training neural networks is computationally intensive, requiring powerful hardware like GPUs or TPUs. While these advancements have made deep learning accessible, they have come with large costs due to energy consumption. Efforts are underway to optimize models and make them more energy efficient, such as with lightweight architecture. Transfer learning allows us to take a pre-trained model and adapt it to a new task. Imagine a network trained to recognize animals being fine-tuned to identify specific dog breeds. This saves time and computational resources. Neural networks have come a long way. Early models were simple and limited, but advancements in deep learning have revolutionized AI applications. Think about how far we've come, from basic pattern recognition to self-driving cars and language models like ChatGPT. With great power comes great responsibility. Should neural networks be used to make decisions about hiring, medical diagnoses, or criminal justice? While they offer incredible capabilities, ethical considerations might guide their application to ensure accuracy and transparency. So, we've covered the structure, how neurons work, how they learn, their processes, the types of networks, activation functions, and even some history and ethics. Together, these concepts unlock a whole world of AI possibilities. And there you have it. Everything you need to know about neural networks in just a few minutes. Thanks for watching. Want to unlock the power of AI? Our free newsletter gives you tips, trends, AI news, and tools you need to succeed. Sign up with the link in the description below. Your journey doesn't stop here. Watch our next video right here and keep building your knowledge.